Okay. Okay. Hello, everyone. I'm Junqi from the from Fudan University. Previously, I got my Ph.D. from Georgia Tech. Today, Huck and I will talk about this one important and very interesting topic about quantum machine learning. We'll talk about the theoretical foundations and also we just introduce some applications of these two devices. So let's get started. In my part, there are about 4 parts. Firstly, I'll show you some background about what is the quantum machine learning, why should I engage in such a topic. Then I'll show you some the 2 important paradigms about quantum machine learning. One is based on variational quantum circuits, and another one is about the quantum kernel learning. In the third part, I will show some applications for speech recognition based on the quantum computing. Maybe Huck next part will show some details about automatic speech recognition based on quantum kernel learning. But in this part, I will show some basic ideas, basic applications about based on variational quantum circuits. In the fourth part, then we will maybe it's going deeper, we will talk about this theoretical foundations of quantum neural network. We show our latest work about this variational quantum circuit-based quantum neural network. Okay, let's get started. This is just outline for today's tutorial. This tutorial will last 2 hours. In the first 45 minutes, I will show my part is later solid foundation of about this quantum computing and quantum computing for machine learning. So let's get started. Okay, everyone very familiar with deep neural network. Deep learning has achieved astonishing improvement.
Is the video still running? Can you hear from June?
No, I cannot hear.
Okay, let me check with him. All right, so seems June is disconnected. Yeah, June, you are mute and disconnected. So would you like to share your screen again?
I think there's a pause.
Yes, you are mute and disconnected. Yeah, now it's good.
Okay. That's not disconnected. I thought that's it's okay now.
Yes.
Okay.
Yeah, please share your screen and keep going. Yeah. Yeah, you should. Are you mute yourself? Yeah.
Okay, it's okay now.
And M2, can you
sorry.
add me as a host? Thanks.
Okay, just a
You can keep going.
Okay, no problem. I want to start about this interruption about the problem on my Wi-Fi. So this is because of the 2 important factors about hardware and it's about the training data. Because we don't care about too much about this theory behind the deep learning. So many people describe this deep learning as alchemy. So maybe it's the engineers from Google, Amazon, and other big companies that is focus on engineering tricks. For example, how to set up this model architecture, how to use optimization algorithms, how to do the regularization to improve the generalization of deep learning for different kinds of machine learning tasks. But our work is a little bit different, and we want to find out is the mystery behind deep learning. So in my thesis during my PhD study at Georgia Tech, with maybe a focus about is why deep learning can work so well in practice. So our finding, our discovery is that if we can set as the deep learning as an over-parameterized neural network, maybe the test loss can go down exponentially. This is very different from the classical machine learning. For classical machine learning, if the model parameters get larger, maybe it's even count. So the classical machine learning it's difficult for them to get out of this overfitting domain. But for the deep neural network, maybe it's, if you can set it as over parameterized setting, maybe it's very maybe it's at some threshold. If it goes go beyond the threshold, maybe this test loss can exponentially going down. This is mystery why this deep learning can work so well in practice. But the problem is that we want to consuming the over parameterized deep neural network. It means that we need to not size model parameters. Okay, so this obstacle is here. So one important obstacle is that the development of this hardware cannot catch up with the development of the demanding for over parameterized neural network. About each 18 months, maybe the number of the model parameters can increase by more than 35 times. But the Moore's law means that for each 18 months, maybe the computational power can be doubled. So there is a big gap between this the over parameterized deep neural network, and there is the Moore's law for development of GPU and CPU. So this is why we are engaging this quantum computing. We will want to make use of quantum power to accelerate this classical AI architecture, because for current this Moore's law maybe is cannot to increase the computational power to support the development of artificial intelligence based on this over parameterized deep neural network. Okay, this is our basic idea about how to do this work. For classical deep neural network, maybe there's a big gap between theoretical study and empirical study, as I mentioned. Maybe it's some people working in large big companies, working in large tech minds, they don't care about the improvement of theoretical study of deep neural network, because maybe they by somehow to fine-tune the model parameters, maybe they can achieve very good performance in practice. But the improvement of maybe some new discovery about the theoretical study of deep neural network have to develop the quantum machine learning. Because currently the quantum machine learning is still in early stage. Early stage means that we only have a few hundreds qubits. So maybe it's currently the theoretical study, the empirical study, and in the same place in the domain of quantum machine learning. So maybe some theory from classical deep learning is very useful for such development of the quantum machine learning. Okay, this the motivation by engaging in this quantum computing for classical artificial intelligence. And next, we'll just briefly introduce the quantum computer. We just use a very brief sentences to describe the quantum mechanics. Okay, these are currently some big companies such as IBM, MQ, and Google. Maybe they set up their own computers. For example, Google, IBM just set up the quantum computers based on the superconducting qubits, and IBM just released its roadmap for the future development. Maybe this year they got released the quantum computer that's based on this ego machine, maybe they call it ego machine, and it currently have us about more than 400 qubits. Last year, it's only about 127 qubits. And maybe they will announce the quantum advantage in 2019, and at that time, it's only about 27 qubits. But next year, maybe it's, if everything goes well, maybe the IBM will release their more advanced quantum computer with more than 1,000 qubits. And in 2025, maybe the qubits number maybe reach about 1 million. At that time, it means that we have a better, much better quantum computer to support many machine learning and finance, and maybe other materials science work. Okay, this is some application plan. Maybe it's the year label for machine learning next year. This year is 2022. Maybe next year, vast majority of the machine learning work can be supported by quantum computer because the requirements for the machine learning, the qubits number is about 40. Only we need a physical qubits, about 40 physical qubits to support vast majority quantum computing, quantum machine learning work based on quantum computing. For more complicated tasks such as finance and machine vision, solar conversion, and maybe it's a drug discovery based on AI technology. Maybe it's need more algorithmic qubits. For example, for the finance, we need about more than 250 algorithmic qubits. So maybe the neighbor year maybe is much longer than this machine learning applications. Maybe it's 2026. But for our topic about the quantum machine learning, maybe next year we'll see exponential growth in such a domain. This is why we just want to introduce, maybe it's just give us a tutorial today, because that's a time we engage in this body in this field. Okay, just what's the difference between this classical computing and quantum computing? I just want to use a picture to describe the difference between the two computing paradigms. For the classical computing, at one time, maybe the computer just want to represent one point in a sphere. But for the quantum computing, maybe we just make use of the superposition and entanglement characteristics. The superposition means that at one time, not only we just represent only one point, instead we can consider all the linear combination, all possible points at one time. So if we run or simulate one experiment, we will consider 2 to the n possible possibilities, 2 to the n possible results, compared with only one result conducted by the classical computing. So this is one difference. It doesn't utilize a super parallel computing capability. And entanglement means that it's only 2 qubits, no matter how far the 2 qubits is. But if there is get entangled, the one state of the qubit can directly affect another qubit, no matter how far the distance of the 2 qubits. Okay, this is the superposition property and the entanglement characteristic involved in quantum computing. We want to use such as characteristic to set up machine learning models. Okay, this is the explanation about this quantum computing. Currently, we're just in the area about the noisy intermediate, also this type of noisy intermediate scale quantum devices. This we call it the NISQ devices. What's the NISQ device? It means that we don't have so many quantum with a quantum base. Inside, so we do have to spare so many quantum base for the error correction. So we have to consider if we do have very noisy qubits, what kind of application we can do now. So this in the future, we expand fault tolerant quantum computing, but now we only have as the NISQ device. So maybe, but unfortunately for quantum computing, for the machine learning application, this NISQ device can support vast majority machine learning applications. Okay, here's from last year, we just introduced our work in so many conference venues. For example, last year, we just want to show our first discovery of our application of how this quantum computing for machine learning in Shanghai. And last year, we have Huck and I as a Huck and the co-host who invite so many experts in such domain to introduce this in this field. maybe this year also we have I'll have to set up some special session in ICASP. When next year we have a new one, so we invite some experts and researchers in different research institutes and the university to participating in our special sessions. Okay. Well, just want a brief introduction to the backgrounds about why should we engage in the quantum computing for machine learning, and what's the quantum mechanics, what's the difference between the classical computing and the quantum computing. And next, I would like to show you two important quantum machine learning algorithms exist nowadays. Maybe you can, these two algorithms are too popular. And I'm going to give a brief introduction about two algorithms. And then the third part, I will show this application for speech recognition based on the variational quantum circuits. Maybe it's a Huck, maybe give you some more examples about this, how to use a quantum kernel learning for speech and NLP applications in the second part. And another part I will show is our latest very fancy work about this end-to-end quantum learning. Okay, so this is a pipeline about the variational quantum circuits based on quantum neural network. So this is first in such architecture, we can see that there are three parts for variational quantum circuit to compose a quantum neural network. The first part we call is tensor product encoding. And what's the tensor product encoding? The function of this tensor product encoding is to convert the classical data y. This y is a non-vector in the classical space. They want to use a tensor product encoding to convert the classical vector into a quantum state. And here, just the quantum state, we consider the superposition, and we consider the entanglement. So here, we just do the data conversion from the classical data into the quantum states. Then we have a parametric quantum circuit. Parametric quantum circuit is very similar to this parametric classical parametric model in machine learning. There is some fine-tuning and adjustable parameters. By fine-tuning these model parameters, we can fit output and input data. So maybe it is a data-driven model. Then finally, there is a measurement operation. Because of the uncertainty of quantum computing, each output of this parametric quantum circuit is uncertain. Maybe with some probability to output by doing the measurement with some probability to maybe output at 0, maybe some probability to output is a minus cat1. So the output, we will take the expectation values. If there's we do measurement many times, maybe the expectation value maybe it becomes a stable value. So we just finally we just connect the classical expectation values as output for post-processing. And post-processing maybe is for the classification task, maybe for the regression task. So this is a basic idea, a basic components to compose the variation quantum circuit. So the first part is tensor product encoding, and the second part is a parametric model. That we call it a quantum parametric model because the parameters is made of the qubits. The finally is a measurement, and down to convert back the quantum states to the classical expectation values. Here it is, we run this experiment many times, maybe it's more over 1,000 times to get expected values. Okay, this is the basic framework about the variational quantum circuit for the composition of this quantum neural network. Here is how to train such as a variational quantum circuit based on quantum neural network. Maybe we just make use of this classical machine learning optimization algorithm. For example, some IDM, STD, various algorithms. This is the CPU-GPU interaction in this training process. CPU is responsible for this what kind of algorithm we choose and how to control this learning rate. And the GPU just stores such a variational quantum circuits. and maybe they also output some measurement classical values to give feedback to the GPU, to the CPU. Okay, that's a very easy implementation of this variation quantum circuit for this new quantum neural network. In 2020, we have a very interesting paper about this part. We suggest the implementation of variation quantum circuit-based quantum neural network for implementation of the reinforcement learning. That's a paper and we get the first reward in Shanghai quantum machine learning competition. This paper has been cited more than 120 times nowadays. So maybe from that time, that's when we start to take more focus and take more time in doing the quantum machine learning. Okay, in this work, we just it's the first time to use a variation quantum circuit to implement this the reinforcement learning. For a classical deep Q learning, maybe that the deep Q learning that replace the lookup table to just build up the input and output relationship between the states and this Q value action. But in our quantum reinforcement learning, we want to replace such a deep Q learning neural network with the architecture shown here. We just use the frequency to replace such as a deep Q learning neural network. And then we want to use the other classical machine learning optimization algorithms just to fine-tune the frequency model parameters. And the experiment that shows that after several hundred episodes, finally we can get a better result in a very simple frozen lake simulation environment. It means for such a simple lake environment, we can also use our dynamic programming to easily find a solution. But here we don't want to use reinforcement learning or maybe the quantum reinforcement learning to find out whether we can use such a quantum computing to find the best solution. And the answer is yes. Even we use only 4 qubits or maybe 5 qubits, if we consider the output, maybe use 5 qubits because really to run some experiment on real quantum computer. This is our work in 2019. Okay, this is the basic idea about this variation quantum circuit, and this introduction about the application about based on quantum reinforcement learning, we can implement the reinforcement learning. Next, just an introduction to quantum kernel learning. Quantum kernel learning is just we call it the very similar to the name, to the title, the kernel learning. So we want to just follow the classical kernel learning paradigm. Only one difference that we don't use the classical kernel. Instead, we want to use a quantum circuits to help us to compute this kernel function. So instead of just find a mapping from the data space to the feature space, you want to find this quantum circuit and to set up the quantum circuit to find a map to form this input space into the quantum hyperbolic space. So this one, without the quantum circuit is like this. Maybe there's UY and the UI is the quantum circuits. Maybe use such even the randomized quantum circuits to speed up the computation speed of the quantum computing. So the output is this quantum kernel value, the quantum kernel values. Images if we run such as experiment many times, they'll take the average. And then the final results very close to the theoretical kernel values. So even if you use the quantum computer, maybe to execute the computation on the kernel learning, maybe the computational complexity can be reduced from n squared to log n. So we think this exponential speed up if we use a quantum computer to calculate the kernel functions, the kernel values. That is a big advantage if you want to use it. Another, if we get these quantum kernel values, we can just use SVM or other kernel methods to find for this classification and regression task. So maybe this is a much more efficient algorithm. And there is one important thing that if we use the kernel method, maybe we just use a quantum kernel space, it have a better representation powers than classical feature space. Why is it like that? Because for the quantum circuits, it has a larger representation capability. We just want to mention that in our last part of my tutorial. So we actually the quantum circuits have a larger representation powers than these than the classical circuits in the feature space. Okay, after the calculation of this quantum kernel, we can just use this perceptron to find out this classification task, to find out do the classification task or do the regression work. Maybe this algorithm, quantum kernel learning is very efficient algorithm nowadays. Maybe they can achieve the state-of-the-art results by using such as a quantum kernel learning paradigm. Okay, this is a basic introduction about these two important quantum machine learning algorithms. One is based on variational quantum circuits, and another one is quantum kernel learning. In this part, I just give you some basic idea about this. And then Huck in the second part give you more examples about the real applications in the computer vision, NLP, and this speech recognition, about how to use such algorithms to set up the real systems. But in my part, in the third part, I'll give you some our brief introduction about these simple applications. How to make more details about it. Okay, the first application is Huck's work in 2020. At that time, we just want to use a random it's a quantum convolutional neural network to feature extraction, about speech feature extraction. Maybe instead of using the time series speech go through the end-to-end occlusive modeling, instead we want to that these speech features go through the quantum convolutional layer. And the quantum convolution layer maybe can be randomized initialized. We don't want to fine-tune such a layer, but we want to use a randomized layer, quantum layer, to feature extraction. So here, as I mentioned in our previous chapter, we see that the quantum circuits has a larger representation power than classical neural network. So when I compare these, we can see that maybe if we use a quantum convolutional neural network, we have as a this cumulative capability based on the quantum convolution encoded features is much better than the classical neural convolution encoded features. Here, feature A is just input mirror spectrogram. It does that the input mirror spectrogram, mirror spectrogram, maybe goes through separately goes through this the first convolutional neural network. The second is a quantum convolutional neural network. We see that maybe the outputs of quantum convolutional neural network features is more discriminative. Okay, so this our paper results, our results maybe can also corroborate our observations. So we just use more full qubits, and the results based on the convolutional encoding, the quantum convolutional encoded features have the best results compared with we use a classical mirror spectrogram features for this based on architecture, or maybe it's also better than we use the convolutional encoding features. So this in this experiment, we want to highlight the most important thing that if you use a quantum convolutional neural network and encoded features, we can have a better represented speech features. Why is that? What's the mystery behind this? And the mystery is that the quantum the quantum models have a larger representation power than classical machine learning deep learning models. That, for example, we use the quantum convolutional neural network. It has a better representation power than the classical convolutional neural network. So this work, we just want to empirically prove that. Okay, this is one example about the application of the quantum machine learning for speech recognition. At that time, only have about 10 qubits. So we don't use this qubits and quantum model to set up the cursor model. And we want to use the representation power capability to set up to extract features because it has better better representation power than classical computing capability. So okay, this is one example about this the quantum machine learning quantum neural network based on variation quantum circuits for ASR. Another one is our last year work. Because at that time we only have about 20 qubits, and in the first application we have about 10 qubits, and then in the second application we have about 20 qubits. So we can make use of the qubits and the quantum model to partially replace the classical based on architecture. So in this work, we consider if we use a quantum neural network to partially replace a deep neural network, and we can follow the pipeline in to see architecture in our hybrid quantum classical neural network, what's the performance like? So in just such architecture, we have used a same model as a pre-trained model, and the QA model just combined with the pre-trained model for our new hybrid model. So in the target task, we just fine-tune the model parameters about quantum neural network, and when we found this convolution neural network. So this here just the architecture about this CN framework. Here we first use to train is the based on his CN pass the DN. A second architecture we just replace the DN with the quantum neural network, and here we just frozen this convolution neural network and only consider the fine-tuning model parameters of the quantum neural network. So last year we have some experiments. If just baseline just a scene pass the DN, a DN for classification, a scene for the feature representation, feature extraction, and then we want to replace this DN with a quantum neural network, and then also use the pre-trained CN. And our result use such architecture, we have even better result compared with the baseline. This the simulation on this GPU CPU environment. This means that we don't consider quantum noise. But if we want to place such a model on a real quantum computer, what's the performance like? Okay, Huck has some comments. Those parameters mentioned here, they are CTC based on our result. Okay, thank you for the recommendation. Okay, so if we want to place the model on a real quantum computer, the performance can be degraded to some extent, but also maybe catch up with the baseline result. Okay, this is our new the hybrid quantum classical neural network for speech recognition, which has published this work last year. Okay, maybe it's a Huck, maybe have more applications about this, how to use this hybrid quantum classical neural network for natural language processing, maybe for the computer vision. But here, just give you one example about how to use it to set up a hybrid model for speech recognition. So here it's just not speech recognition. That's speech command recognition. Maybe it's a little bit different between speech recognition and speech command recognition. Okay. Okay, we just give two examples of the use of this variational quantum circuit for in practical speech processing applications. But there's some problems existed for this variational quantum circuit based on models. One obstacle is that limited representation capability if the target function is non-smooth, is non-convex, because the unitary the variational quantum circuits that correspond to the unitary transformation. Unitary is a unitary transformation, just a linear transformation. So this if the target function is non-smooth, then we come non-convex function. Maybe it's how to boost the representation power of such as a variational quantum circuit is one obstacle. It's one our concern. The second one is that the barren plateau optimization problem. Barren plateau means that ideally, even if one want to optimize the VQC-based quantum neural network, there indeed is one path from the bottom of a mountain to the top of a mountain. We want to find such a path to optimize the graduation quantum circuit. But in practice, we can't find such a path. Instead, always stay on the horizontal line. It means that also we do so many fine-tuning process, but the Tesla laws cannot degrade it. Cannot be lowered to a small scale. Also, but we also maintain to a very large Tesla laws. So it's a stay on the horizontal line. There's a problem we call it the barren plateau. So how to overcome such a barren plateau problem? In our latest MPJ paper is a Nature paper. So Huck and I just released this Nature paper to just introduce some new algorithms, new methodology to overcome the barren plateau problem and how to boost the representation power in practice. Okay, just the last part, I'll just introduce our Nature paper. In this work, we also focus two important improvements compared with the obstacles. Focus obstacles of the previous VQC-based quantum neural network. One is how to introduce nonlinearity to this the VQC, because you can see is as a unitary linear transformation from the input quantum states to the output quantum states. So how to introduce the nonlinearity? The second important issue is how to overcome the optimization problem we call it barren plateau. So that's why we just introduced such a model. We call it a TTN VQC model. The TTN is a temperature model. The temperature model is commonly used in machine learning. There's originally from the mechanical, it's a classical mechanics in physical domain. Now, in the recent work, there are so many the use of temperature network for the feature dimensionality reduction. Maybe it's just use a temperature for classification task. Here, we just not only simply to introduce a temperature network, we want to introduce temperature network, only one layer temperature network, only one layer temperature layer to impose the nonlinearity to this VQC model. And this, just as I mentioned, there are three parts of VQC model: the tether product encoding for feature, quantum feature extraction, and then it's a parametric circuit for just with adjustable qubits. And finally, this measurement to output castle expectation values. Okay, then we want to focus. That's the first important thing that we need to introduce such architecture. We just introduce how to use the temperature network to impose the nonlinearity to boost the representation power of the VQC model. And the second thing that was kind of set up to overcome the barren obstacle optimization problem. And then we want to focus the Tesla laws. Tesla laws is bounded by the sum of three components. One is the error of representation power, as representation loss. The second one is estimation loss. And the third one is optimization loss. So we separately to see each loss, what's the factor determine this each loss, and how to further upper bound each loss. Okay, first important thing that we want to introduce one layer and the train layer. It's maybe temperature in the classical machine learning and classical deep learning. You can reshape the fully connected layer into the temperature format. And if we do that, maybe it's we can use a much smaller model parameters to maintain the the baseline performance. I will have several important several interesting paper for speech classification, for the speech recognition, for speech enhancement based on temperature neural network. And more importantly, the temperature layer can physically find equivalent quantum circuit to send it to place on is a real quantum computer. It means that for a classical neural network, it's incredible to find the quantum circuits to represent it. But if the fully connected layer of the classical neural network can be converted into the tensor train network, we can find equivalent quantum circuits to represent the tensor train layer. So in such an architecture, in practice, we can find out is an untrained quantum architecture. So there's no classical neural network get involved in such architecture. Instead, we only use all the quantum circuits to represent to realize such as quantum circuits. Okay, this give you my example. For example, if we want to consider this tensor train layer, we can use equivalent quantum circuits to represent this classical tensor train layer. I use such as this equivalent quantum circuits to compose this the one layer of tensor train layer. So this variational quantum circuit is the tensor layers. We can compose of tensor layers, and such as it also can be composed of quantum circuits. So from the beginning of input to the final output is end-to-end quantum, totally is quantum model. There's no classical model involved. So that's consider that classically for the classification task, we use the hybrid model. The hybrid model, some model from classical neural network, and the final classification is based on the quantum neural network. And in this work, from the very beginning to the end, we just the whole pipeline is based on the quantum models. We don't use the classical model at all. So this is a very interesting thing. That's why we just want to introduce this the tensor train layer for the feature to add some nonlinearity in the feature here for the feature space, and also we just use it for the quantum implementation. Okay, so the end-to-end quantum neural network. Okay, this give you some theoretical understanding about this our TTM frequency. TTM means that it's just a tensor train layer for the feature dimensionality reduction and the feature and introduce some nonlinearity to the feature in the feature space. And frequency is just the classical frequency model. And then firstly, we consider representation power. And then our finding is that it's just the upper bound is very inversely proportional to the number of qubits. And it also is very related, inversely related to the constant measurement. It means that if you have more qubits, maybe it's currently we use 20 qubits, you have more than 100 qubits. The representation error can be further reduced to a small scale. And if you want to do more measurement, it means I have a more stable expectation output for the post processing. Maybe representation power for the TTM frequency model can be further improved. Okay, this is the simulation based on the different qubits. Where we use the simple 8 qubits and the 12 qubits. We just compare that if we use the 12 qubits, the MAE loss for regression work can be even further reduced. Okay, another thing more important is about generalization power. Generalization power maybe is more related to the training data. The training data is the target quantum data, and also maybe is related to the quantum waves. Ideally, we just want to set up is over parameter setting, but in practice, it's incredible to do that. So maybe instead, we just consider if we can set up this model as to satisfy the PL condition, we can better overcome the obstacle of a Baron-Pareto obstacle problem in the process optimization. So here that you do have the PL condition set up. Maybe when we found this Baron-Pareto problem because the test laws just stay in the same horizontal line. It means that we just fine-tune the model parameters many times, but test laws is still at a very high level. But if one want to really satisfy this PL condition, maybe this test laws can be go down to a small scale. So the problem here is that how to set up PL condition. In this work, we think our model satisfy the PR condition. Because if we want to set up as an over-parameter setting, we can easily just find the setup for the PR condition. But in many applications, how to set up, this is one important concern. And our finding is that you can make use of pre-trained model. Yeah, if you use, for example, that's our previous work, we use the same as a pre-trained model as the initialization for the hybrid model. If you use, make think about how you use the pre-trained model at the startup, maybe it's we can easily find this set of PR condition for better overcome the barren Prado problem. It's our new finding. I'll still do some theoretical work. But one empirical studies to support this work is for our application about for speech recognition. We just find maybe it's a pre-trained the same model. I use a same model for feature representation. Maybe if we only consider fine-tuning this the quantum neural network, maybe it's, we achieve even better result. So this is a very interesting thing. So in our work, we may consider to pre-train this tensor train layer instead at the very beginning. So here we just is end-to-end training. It's a very from scratch. We just to train this tensor train layer and the variation point circuit. Maybe if we can retrain this tensor train network, we can better to find, better to satisfy. It's easier for us to satisfy the PR condition, so we can better overcome a better problem in the training process. Okay, this is our finding and some brief introduction of new theories in our Nature paper. Okay, maybe it's just end of my part, and Huck will give more examples based on quantum kernel learning for speech recognition and for natural language processing and for computer vision. Okay, this ends my part. Thank you so much. Thank you for your attention. Thank you so much. Okay.
All right, so thank you, Jun, for this theoretical foundation. And are there any questions? Yeah.
Hansen has some question.
Yeah, no, actually, sorry, not a question. I actually just want to make a comment because I attended Jun's last seminar, and I asked a question about the kernel, quantum kernel, why it assumes the particular form that it does.
Okay.
Your slides. Yeah, that one, the equation 2. So basically, if you don't have the norm squared, it's still the kernel. So the inner product would be a kernel. So actually, I did some research. So basically, the norm squared can learn the quantum infinite deep quantum neural net. So this is a result actually just published by Caltech's
Robert paper.
Robert Huang, sorry, not Robert Yang, Huang, the entitled Power of Data in Quantum Machine Learning. So it has the theoretical the derivation of the result. The whole paper is basically about why the quantum kernel, the squared quantum kernel, is more powerful, and particularly proposition 3. So that was a pretty kind of deep result. I just want to mention that. Thanks.
Okay, thank you for this the comments for this part. Thank you so much. Okay, but Huck have more contents to introduce. So maybe it's the time is given to Huck. Maybe you can start it. I'll just stop my share and you can start your work.
Okay.
Thank you.
If you have other questions, like you can post in the chat room, and after my part, we can still have some time, like Jun answer, so I will answer those questions. All right, so let's have the second pass, second part of this. Right. How to share it? Sure. Okay. That it looks like I have some access issues. All right. Let me share the screen. Can you see my screen right now?
Okay, no problem.
Okay, cool. Okay, let me find the slide. All right. So hi everyone, welcome to the second part of this tutorial, quantum machine learning for speech and language processing. So for my part, there'll be application and some practice feeling when we do this kind of research related to quantum machine learning. So before I start my talk, I want to give an overview about quantum machine learning as a solution from 2018 to 2023. So if you look like this diagram, we can find that mostly consider a speech recognition task from CTC to RN transducer and the joint supervised and unsupervised ASR like JOST. So we can see there is performance boosting, right, like year by year. So right now we take advantage from this DNN-based architecture. But meanwhile, if we look at this figure, on the orthogonal of this axis, we also have some kind of characteristics driven task. For example, we want to reduce time capacity, sample capacity, improve data encryption, and somehow improve security issues. So I would say some of the work is trying to addressing these issues not come from one orthogonal like result, trying to combine some quantum property. For example, like our work in ICAS 2021, we use a quantum encoder, but that encoder is in a separate machine. And to do this data isolation and trying to improve some security condition. And in the CVPR 2022, there's another paper like simulate image patches as a token with a weight function that outperform the swing transformer. So I would say this kind of research got this inspiration from quantum, but the model is not fully quantum machine learning based model. But we can see by incorporating a little bit about this quantum property, like our model can get both have improvement on the performance driven task and also adding some ingredient on some special using condition. But meanwhile, I would say if you coming from a quantum computing community, the main challenge and the big challenge you want to resolve is still more fundamental. For example, we do know before 2000s, there's in 19s, there's some original paper describe how to use quantum algorithm to classify phoneme. And more recently, in Google, they have a quantum supremacy paper. So for those models, they are purely quantum, and the problem they're gonna tackle is like it's hard to reserve on the classic machine. So in this way, this push the horizon about the task we can reserve. So now we can, when we look at this solution, we can actually, when we mention quantum machine learning, which is take advantage quantum computing, right now, due to the hardware constraint, we could not directly do those problems like the red dots, like the purely quantum circuit or quantum kernel things. But meanwhile, the hardware like revolution is pretty fast. Like you can think about like a decade ago when people working on DNN, so we can actually do some pioneer work trying to combine these things together. So for today's talk, I will give some recent example how and where people can conduct research. I mean, like if we consider as a researcher, we want to step in this new quantum machine learning community or trying to doing some quantum machine learning application, I would say right now it's not purely performance driven task. For example, if you really want to use a pure quantum model, the thing you can deal with is actually molecular data and some quantum format data, which is a popular track in New Reach and ISML since this year. as a speed researcher, right now, we are more focused on production-driven task. So I would say here is something we should focus and look at during today's talk. So again, I want to mention some fundamental question. So why should we do quantum machine learning research? Let's say maybe next year. So I would say we're trying to reserve some question that cannot be done with classic CPU. For example, with quantum machine and quantum simulate QPU, we can actually dealing with the data with complex phase information, and we can process this quantum format data directly. And the second thing why we do this kind of research is we're trying to incorporate this quantum property into deep learning solution. That's for example, I say by using quantum machine, you projecting those features in a high dimensional hyperparticle ball, so you can have a better representation power when you separate those features, and you can do the encryption and data isolation, which could not be done with the classic algorithm. And another question I would say a lot of researchers are interested, maybe mostly today, is how can we do quantum machine learning in 2023? I would say mostly there is some CPU-based QPU simulation. Right now, actually, there is a TensorFlow quantum package, which you can directly do some quantum circuit training and even train with means with your quantum-based model directly. And meanwhile, there's also a PyTorch based solution called Pennyline. I would say you can first use a CPU-based QPU simulation for your work. And also they have TPU-based simulation. For example, you have ASIC, which trying to accelerate this tensor computation progress when you do this quantum simulation. Finally, for the real application, there will be Q-ski and BNQ. That is for the real quantum machine. So I hope if you get nothing from this tutorial, these 2 pages help you understand what kind of research we can do and what the thing we're going to talk in the following maybe 1 hour. All right, so as an example, I'm saying, okay, so there is some preliminary work, how this work look like. So I would say right now in recent 2 years, quantum mainly be considered as a feature extraction for both acoustic and language information. For example, you project those acoustic feature and language embedding the latent space, and then by having this projection, people find out, okay, there is some slight improvement when you certainly mapping back this feature with your classic classification algorithm. I will talk about this detail, but it's one kind of main category. And also there's a quantum as hyperplane modeling for kernel learning. Right now, there is one paper for speech recognition just released today. Is one of my side project when I was interning Google. So we find out, okay, with quantum kernel learning, we can do this kind of separation for low resource language. And also, thank you, my advisor, Professor Lee, when we do this kind of research. And the third part is another thing right now is adding some nonlinearity for hyper quantum classic modeling. I would say quantum is a tool when we mapping this data in the high dimension space and mapping back. But meanwhile, there's some recent discussion saying, okay, this mapping is actually don't have this kind of nonlinear transform. So there's some paper just discussion these issues, like June's discussion and one paper in NeurIPS last year. So I would say these 3 kind of main category way you can do this kind of research. So the first one is kind of low-hanging fruit, and the following 2 is much fundamental. I'm going to review that. All right. So in this 1 hour, so first I will talk about the background about quantum computing and why did quantum computing motivate us to kind of revolutionize some new design for machine learning. And the second, we're going to talk about quantum machine learning to a perspective of representation learning. And finally, I will provide some little bit implementation saying how we can implement those hybrid quantum machine learning as a part of this tutorial. So I would say, since we still have time, so if you have question, you can leave your question in the chat room and I will try to answer that even after this tutorial. Okay, so let's go to the first part. So the background would say what kind of data and algorithm we are looking today. So for when we talk about quantum machine learning, there are actually different diagram we can look at. For example, the data can be quantum like this, but the algorithm can be also quantum. And for the classic algorithm we're gonna dealing with is actually the data is a classic format. Classic format means like 0 and 1 and in the bit format, and algorithm is also in the bit format. And for the red one, you can think of some physical data have to use some specific like high dimension methods you're dealing with. But we also look at today is actually the data is quantum, and people use some classic algorithm like deep neural network to dealing with this black hole data. That's one example. But what we look at today is we have some classic data like speech and language corpus, but can we use some quantum algorithm to dealing with this classic data? So they have some advantage. For example, we can have some quantum speed up and large repetition space and memory and model capacity advantage depends on how you design and select your hardware. But also we also have some disadvantage. So one well-known disadvantage is some of the quantum hardware is not really ready yet. So once you're doing the simulation, the result is really good. But when you apply the real quantum machine and the quantum qubit larger than 30 qubits, the performance will have a lot of sensitivity issues and large error bar. So I will cover these issues later. But as some advantage we look at mainly today is for the large representation space and some potential like hyper computation architecture, which can be good for speech and language processing. Let's say what is quantum exactly? So when we look at a vector, we can find out in the quantum space there's a Bosch vector. So which is you consider a qubit between 0 and 1, chi 0 and chi 1, and there is some probability density between this ball, and you will only have your actual value once you're doing the measurement. So the background is while these things can actually speed our classic computation. But it is a paper called Quantum Machine Learning in Nature 2017. What these things have a good summary is by incorporating a fully quantum machine learning. So in doing this update process, they will have some speed up. For example, when we consider MTT application, HACL algorithm, so this is used to be serving linear system and the quantum random access memory. So this is related to how you select your QPU. And we can find out you can do different things with a purely quantum algorithm. For example, Bayesian inference, online perception, least square fitting, classic like Boltzmann machine, quantum PCA, quantum SVN, and quantum reinforced learning. So they will actually have some speed up based on this algorithm design inside this quantum random access memory. But today we more coming from the algorithm perspective, but here just give you a taste saying, okay, even those classical algorithm can have a quadratic speed up with the sample size of n. So why especially today this quantum machine learning become a hot topic instead of research project or something working in the future? We can look at a figure like here. So this figure is sourcing from a 2016 paper in International Conference on Computing Frontier. So in this paper, they expect there's a convergence between this quantum software and the quantum hardware. So what this convergence means, like for example, when the hardware is little processed, we couldn't really do a real algorithm based on this only simulated result. And then expect around 2025, you can actually have a Q acceleration with those kind of quantum rods on the machine, and eventually become converge around 2013. So right now, I think we are around here, and no matter what we are listening today with this kind of interest, you're actually in a really pioneer stage. So the open question could be, okay, since we expect they'll all be converging one day, but when these things can actually converge, do we have some data point to support these things if we want to initiate this kind of research? So here are some data points saying how recent the qubit is actually become large and accessible for the commercial level and even for some school level. So when we look at this qubit, I mean, the quantum computer in 1998, there's only 2 computable qubit in the machine. And then gradually we can find out in 2017, these things become scale up to 50. And year by year, they become 128, and even in IBM, they expected this year like covered in 400, but eventually got around 200 to 300, but still a large number. And back to the topic, I want to do the quantum machine learning today. Can I really access this quantum machine? The short answer is yes. So IBM actually offer a 5 qubit and 10 qubit machine for few access. Okay, under this background, we know these things really converge from hardware progress. But why we have to doing this kind of research at this moment? So this coming from a perspective called the noisy intermediate scale quantum. That means right now we are in, when we do this computing, we're actually in the cosmic world. And there is some desert, like if you want to directly using this quantum machine. And here is some wall we couldn't directly go with because this hardware constraint. But it's possible after this desert, you can just try to implement some preliminary result on the machine, for example, with 10 or 20 qubit and demonstrate, okay, this algorithm can potentially good when the hardware even gets scaled up. So here is the philosophy here and why we should do this hybrid cosmic and quantum algorithm at this moment. Another thing support this philosophy is actually coming from Google's AI blog in 2018. So they also have an idea saying here we have different numbers of qubit. If we really have like saying 10,000 qubit, they are useful for an error collect quantum computing. And right now we got around from 10 to I would say 1,000. So these things is right now we are needing the near-term application. So saying if we're doing research here, eventually we gotta have big impact here. And that's why and the reason we're doing the quantum machine learning research at this moment. And we have example for speech and language processing. There's actually more discussion, but since this is a taster, I will like to motivate people working on this problem. Like the problem could be is quantum advantage is a right goal for quantum machine learning. Saying we do know there's some quantum advantage, right? So like Google's paper, they can resolve the traveling salesman problem. But meanwhile, in the quantum machine learning, people are really look at is to search a quantum perception, saying what kind of quantum machine we can get, and once we get a certain computable quantum machine, can we design neural network or a quantum circuit? Quantum circuit, that means a tensor network, and which train like by gradient shifting. I will cover later. But how to design those kind of heuristic architecture is one open question just right now. And the second part is to have this connection between quantum circuit and general learning theory. So this is something Jun just covered. And third part, I would say, is more something I like because quantum is not the focus of my thesis. So the thing I'm much familiar is like to support some quantum hardware and like to implement some quantum application as a taster. So I would say these three questions are all important, and then it depends on how your expertise and your interest to develop your research align one of this mainstream. So yeah, so in this paper, they actually justify, okay, saying in some way the kernel learning is similar to quantum computing, and I will now cover the detail. You can look at this paper. All right, so that's some take-home message before you're falling to sleep. So I would say, with the rapid development of quantum hardware, understanding and designing quantum or quantum-inspired algorithms is an emerging issues. And second, near-term quantum algorithms could be the current goal running on near-term quantum computers. I would say, you can consider you can do some toys, speech and language processing with this hybrid algorithm, but potentially once you find out some new combination or some architecture design, they can be really impactful. Like the early year, people can design ResNet or just temporal convolution and get a really good impact to the community. They are not trivial work because this diagram and the representation are quite different. And finally, I would say quantum machine learning has different goals from its theoretical perspective to application. It depends on what you want to combine this analysis. And right now, this theoretical analysis is basically bare and almost empty. All right, so after we have this background and knowing we should focus on this near-term intermediate quantum algorithm and what kind of quantum machine learning we do have, like before the term calling quantum circuit learning, and why is quantum circuit learning and why we're gonna select this quantum circuit learning currently. So let's look at some work before, saying 5 years ago or even 10 years ago, mostly right now. So before like in ACL 2020, 2013, 2017, there is still some attempt to use quantum computing combined with natural language processing. But their main idea is to improve sample capacity when you do this kind of quantum simulation doing the language modeling. For example, the token and the sample trying to compute. Another thing is trying to model in the turn dependency with quantum language model. So we'll cover these things, but their idea is not to running these things on your machine directly, but in the algorithm itself, trying to reduce the sample capacity. For example, quantum modeling for both single and compound terms as a density matrix. Density matrix is one kind of mathematical formula in the quantum machine. So their idea can be, I have a single sentence representation once we have some sentence matrix like this, and then we can have our product to product these things. So it's a density matrix. So density matrix is computed in a quantum format. You can think of the include some complex value, and then you can put this sentence matrix at the outer product, and then to have a general representation when you do the convolution in your network. So here you can see this is actually inspired by quantum, but not actually have to run on the quantum machine. The main idea is they use the density matrix to get some complex information. So this is paper published in III 2018, which achieved a state-of-the-art result for compound modeling. Meanwhile, if we look at the newspaper in ACL 13, the idea is trying to have a compositional model, which is also quantum to reduce the propensity. So we can find out they are not focusing on gradient propagation-based training and learning, and they're also pros and cons to avoid. But eventually, we can see by directly imply quantum in those kind of algorithms, simple capacity is something we can really focus. And more recently, this quantum-inspired algorithm. Inspire means like the algorithm not necessarily running on the machine. They also have good result on some classic tasks like image classification. I will highlight one work in CVPR this year. They call the image patch is a wave, face-aware vision MLP. So their idea is to have a multi-layer perception, which is an MLP. But between these layer norm, they will have a process called a token mixing. The token mixing will simulate this input token with amplitude as a phase, and then they will have a phase away token mixing as a weight function, and eventually the output will mixing from the real part and the imaginary part. This is something interesting. Like this process can be eventually run on a quantum machine and get on speed up. But right now, even on CPU, you can get this thing compute directly. The output you got is the outcome you got actually is a better representation when you do this MLP training. And their result, I think, is on the open benchmark, at least for 2 or 3 months, and better than the swing transformer. Okay, now we see there is some solution with quantum-inspired algorithm. But what is the quantum circuit algorithm, which are yet covered, and how we can apply this quantum circuit algorithm with hybrid classic and quantum machine learning. So the background about vibrational quantum algorithms is like this. Vibrational quantum algorithm, that means like the training progress associated with the vibrational training process. The vibrational is not directly related to the vibrational inference in the scientific community, but I will illustrate later. So there's actually different optimizer before this quantum circuit training coming up. Basically, you can think a problem like this. So I have some theta, which is a trainable parameter here, and we mapping this theta to a tau, which is a quantum computing operator here, and then eventually you can get your actual value and the optimized things you want to optimize, and then you just compute a loss function with gradient as a classic algorithm. But here we don't have this graphical connection, right? So one thing we can really do is to add a small perturbation in your input and output to have this gradient shifting, and then you can have this like shifting based gradient update and when we train this algorithm. And the drawback is, it's not broad propagation. The comparator is not really good, but you can still do the end-to-end training. So there's 3 different ways consider this end-to-end training for quantum circuit learning. So the first one called the similar annealing. So the idea is you have a fixed weight by you trying to minimize this weight times your functions by your algorithm. So you're trying to minimize these things by finding a theta here. And the second is the echo state network. So you have a input, which is a chi0 and over some quantum machine, and you can see there's a fixed parameter. But here is you're not going to find this theta here. You're going to find a weight matrix here. And finally, they call these things like a neural network, which is a quantum circuit learning, QCL. You still have a chi0 here. Chi0 is like you have some classic data and with some quantum encoding, you mapping back to quantum space. And you go over one circuit and another circuit. So eventually you can try to have your loss function about your original F and another quantum circuit which controlled by your theta here. But what is the quantum circuit here? You can think of in neural network, we do this feature mapping. But in the quantum circuit, there's actually a vector in the high dimension space. But this theta just control this vector to mapping to the right direction and eventually have a low prediction loss. So the first one, as a conclusion, is minimize the output of the quantum circuit. And the second one is tuning the weight. And the final one is tuning the quantum, the circuit parameter. So that's why these things is similar to neural network, right? So we have something to control as entirely with the theta. So I would say the first work consider this format as a neural network and training with quantum circuit is from Kohn, ETL, and their collaborator. So their idea is once we have the input of image data, they do the convolution and do the pooling and do the fully connected again. So this paper is actually got really high impact since they published in 2018. And then if you turn out this process, consider as quantum circuit learning. So in the neural network, we have this connection. And in the quantum circuit, there's something similar by wiring these things together. You can think of this just a special component, which is similar in the neural network. So for example, this component can be used for pooling your data, and this component can be used to make this convolution. And eventually you can do another operator for fully connected, and finally you got the output. So here is kind of measurement. So one thing here, I will say how this quantum-based layer construction eventually make a quantum enhanced transformer. So first, I want to talk about our work with Jun together, and this work is actually during one of my holiday back to Taiwan. I meet my friend, Dr. Samuel Chen. So he has some issue to write some reinforced learning code. And I just helping to write the reinforced learning code. And he told me this time he didn't use the neural network layer to optimize the loss function. Instead, he used a formula like this. You can see here the R is kind of rotation gate. And R theta 1 and phi 1 is those kind of rotation to mapping your classic state value to the quantum space. And then you have a R alpha, beta, and gamma. those things represent the general single bit unitary gate with 3 trainable parameters. So here the trainable parameters is alpha, beta, and gamma. And then you just trying to rotate this angle and eventually train your model. In this turnout, you only have a few trainable parameters, but you can still do this high dimension space mapping from your caustic to your caustic data to your quantum data. And reinforced learning is exactly a good playground, because reinforced learning will only have a really small state data, and the whole thing you want to optimize is just your reward as a one bit, so one digit thing you're trying to optimize eventually. And once we know these things actually just replace some layer in the caustic neural network, like the dense layer. So in the ICAS 2022, there's a paper called The Dawn of Quantum Natural Language Processing. They just take this idea to make this layer. We all know, like in the transformer, we have a key, current, and value, right? So now we can actually define it for a quantum circuit here. And by having this embedding and have this entangle layer and have this like trainable rotation gate as I just introduced, and you define this thing as a basic layer. And each time when you compute key, current, and value, you just code this layer, and finally the things will be trainable, and you can have your quantum transformer as a result. So the fact, so now we know these things can be trained perfectly with your quantum machine learning, and you can construct these things with a layer. Although the layer is not ideally understand as a neural network layer, but it's something trainable and can be trained with the gradient from an end-to-end fashion. But there is some bitter lesson when we do this kind of research. So even caustic to quantum encoding process actually take exclusive time. For example, you want to train a 60,000 mean samples, they will take usually 500 to 700 CPU hours. So usually these things take 20 to 30 days to complete one experiment. If you want to train these things by gradient fully. And the gradient shifting algorithm, I mean, because we don't have the backpropagate on this black box, parameterless black box, right? So you have to use gradient shifting, and each time you get some shifting parameter and to find out your gradient. So these things you will even take longer if you do this iterative training. So after knowing this fact, which constrained by the current quantum machine, because we're doing the CPU-based simulation, could we actually have some options saying, can we skip the training time, but only have this quantum caustic to quantum mapping? So here's come to the idea. I would say is the economic solution. So this time they introduced a random, which is a non-trainable circuit learning. So each time, once we have a data, like if you're familiar from signal processing, we do the convolution. It's actually we pick out a n by n kernel, and the n by n kernel while trying to compute with some weight matrix. But why not we just using a random circuit, which the theta of this gate is random initialized, but we only take advantage of this random mapping, but this mapping will be happening in the quantum space. This paper in the Quantum Machine Intelligence in 2020, they find out if you just apply a random initialized quantum circuit and you don't train this quantum circuit, just use it as a random feature structure, you can still train a model and even perform better than the 2x2 neural network kernel at the same time. So their idea is like each time this window will go over input data and to form a computation diagram like this. So the output will generate these things called a quantum convolution. So you can control your channel output. And then the pooling convolution, the pooling 2, and the fully connected are all made by the neural network. So the only thing you take advantage is this kind of representation, mapping by caustic to quantum and mapping from quantum to caustic again. So from their result, you can find out compared to CNN, QNN, and random initialized QNN, you can find out the performance is actually much better compared to CNN-based solution directly. And the QNN and random QNN, in some cases, the performance is even similar and as this kind of result. So after finding this paper, the intuition is like, can we apply for speech? So I would say I thank my advisor, Professor Qinghui Li, to let me try these things. Like at least we tried for 1 or 2 months, And our idea is trying to, okay, can we also consider feature extraction for speech processing? But I get a good advice from Professor Lee saying, if you directly do the feature extraction, they didn't take any quantum property. Then we just reanalyze this problem. And we find out the problem for quantum computing is you can allocate this quantum feature in another instant. For example, when you do the feature extraction, you can actually put it on the cloud and the local model, they use in other features. So here is a summary saying the overall machine learning approach and really key components. For a classic model, you have input as bits, and the learner, the learning model is DNN and something else, and the output is also bit. But one thing for hybrid quantum model is the input is bit, the output is bit still, but you in the intermediate layer, you can put something for quantum, and you can put it in the different instant for the security issues or privacy preserving issues. So finally, property is accessible quantum advantage over the vertical filter learning. All right, so it's motivated from to the same things on the data protection, like the GDPR or CCPA. So then the computation diagrams like this. First, we have a local user, and we put this quantum convolution on another instance, for example, IBM instance on the cloud. And then you just so the local user will not have like, we will not have this, the feature from the local user, and the local machine will only, for example, your cell phone only have the decoder feature from your quantum encode results. And then you can do the continuous speech recognition or the speech command classification. And we also, as a first work, we should be responsible to analyze this result. We find out from different channel of this quantum compute like layer, they actually learn different representation from high frequency to low frequency. So these things are render initialized is not even trainable. So which is surprise to us. Another thing is like compared to 2x2 neuron convolution based encoded, like the quantum convolute encoded is actually have a similar representation, but this thing is really sensitive to window size you select. Another thing we find out, but we didn't put in the paper, is the training time. If you want to train the model, it's not render initialized. For example, you want to train this 4QE based model with TensorFlow. They're actually much stable because you have least trainable parameter, which is more intuitively. Right, so after that, like Professor Tao also apply another work following our work. So in our work, like we put this the quantum convolution as a feature encoder, right? But you can also apply the pre-trained model like the BERT model, and you can put this quantum convolution things as a decoder between you put into the classifier. So their idea is to apply quantum temporal convolution. And then, for example, for each time you have an input sequence, you can just compute these things in one-dimensional kernel, and then you can do the global max pooling to carry a final feature. As I say, it's early age, and they are blue sea. They don't even have a quantum temporal convolution yet. So this work also got accepted to ICAP 2022. So now we know like feature extraction is one mainstream for computation perspective on some early taster for speech and language processing. And there's a lot of following work from the paper in the ICAS 2021. And yeah, I know the Ping An Bank, they even publish a toolkit to do this feature extraction, but I will cover it later due to the time constraint. But I would say like once we know the feature extraction is good, but if you look at the performance is not improved a lot, right? So you got some improvement, but the improvement just 0.0 something, and the maximum we got after close validation is like 0.1 or 0.8. Another thing I want to deal with is like we know the hybrid model can give some performance-based improvement, but I would say the main property is still the property come from the quantum, you know, like the data isolation and the security reason. So another thing people look at the near-term quantum NLP is to use variational circuit to model in grammar construction. So that means in the classic compositional language model, we have this relation like compute by some computational operator, but you can only use these things you can also use a quantum circuit to compute this relation. So in their work, they are defined a variable of Alice and Bob, and they are both variable both by the quantum circuit. And since they are pure quantum like model, so you can do this computation pretty fast in the compositional level. For example, the black hat, you can model in these things with a relation like this, and then you have your quantum circuit to model in this black hat, and you can separate these things with hat and black by two notation in the quantum circuit. So for detail, you can look at this paper from Cambridge Quantum Computing. But they find out you can actually use this computation logic to do a neuron competition model and to have a SOTA result, and they release their code and implementation. All right, so finally, I will talk something on the quantum kernel learning and give some basic here. I think as the previous discussion, like the effective of quantum circuit learning based on the Robert Huang's like Nature Communication paper in 2021, and here is a following paper gave a more concrete idea like how we can compute these things in practice. So for kernel learning, now it's not a fancy term, but we know the kernel just trying to separate the data, right? So for example, we have two groups of data. In this case, they are in the plural classification. But we know it's pretty hard to find this real separation from the blue and orange like this. But ideally, if I have a kernel in the high dimension space, we can actually separate this thing properly. But how to design the kernel like that, and how this kernel relate to the quantum computing? That's something I'm gonna cover in this 5 to 10 minutes. So in the linear classification, we actually trying to have a hyperplanet, which is controlled by the weight here to separate this two group of data. So with a vector W here, which is orthogonal to it. So for example, we can assign a classic label Y to adapt a data point like by this. So it's a classic format about a support vector machine or regression-based prediction. And then once we have a W plot living in the feature space corresponding to a feature map, we can write in this format into here. Here is the inner product of the two vector. So, but the optimal decision boundary about the equation 2 can be actually compute of a sum of the embedding data point of the real coefficients, which can be computed by this term. So we can rewrite this term by the ratio of alpha and times to this phi xi and phi x. So this term is actually something we can model in by quantum kernel. For example, the quantum kernel just mapping something from the classic to quantum, and we can have a kernel like here, and to mapping our data from quantum to kernel to find our ideal space for separation. So here's the idea. So you can have your embedding, and finally, with this kernel embedding, you can make your decision eventually. And I think following some discussion later, so this norm is important, but here is a general format. And how these things computing in the quantum space, they have some details. You can refer to this paper. They give a really good instruction and step-by-step derivative. All right, so after find out these things, in the summer, we find out after I done my main work in Google, I still have some bandwidth. So with Dr. Bowley and Yu Zhang, we also tried out, can we use the quantum kernel learning to deal with some low resource speech classification? And I got some a lot of suggestions from Professor Lee to refine this problem. So the problem become once we have a low resource speech, we can pick out some acoustic feature, and then we do the quantum circuit based encoding again. And these things will have some distant matrix measurement by kernel. And then once we have a kernel learning, we can apply this kernel matrix learning and to separate this space with the kernel. And eventually we can see if these things can get a good result. So for this part, they can actually compute by the quantum space with tensor TPU-based simulation, which can accelerate this computation. So we find out interestingly, first we just cut up the Google speech command for the classification. We find out if we deduct the data down to 5,000 K, the kernel-based projection actually perform better than some quantum convolution-based algorithm and the pure DNN and the kernel matrix learning. And these things can be even good for some low resource language we collect. For example, those languages are smaller than 1,000 utterance, like Georgian, Kovacic, Lithuanian, and Arabic. And one thing I find out interestingly, which you can also find out from Robert Huang's paper. So in the quantum kernel training, for the training and for the training apples and accuracy, they are similar to the DNN. But for the testing, in some sense, they will perform better than DNN, and the result will be really stable because they have least trainable parameter. So I will give a link to how you can train these things with MNIST. But there's something we find out is if you apply quantum kernel learning, the standard deviation about train your low resource data will be much small. All right, so now we know the quantum kernel learning is another alternative, like compared with feature instruction-based training. So in ICAS last year, people from computer vision also applied this idea, saying we can model in this diagram by a kernel correlation loss, which is classic loss for some three-dimension computation, three-dimensional computer vision. And then you can model in some complex things like in 3 dimension with your quantum circuit. That means you can have a phase information here, and when we use quantum circuit to form your kernel and then do the kernel-based training. So you can find their code implementation here from the Cambridge University. And here's some result. You can come in and make these quantum kernel for optimal transfer perspective and to calculate MMD loss. And finally, yeah, I think as the previous discussion in the first section, in Robert Huang's paper in Nature Communication 2021, right now we are in the early stage doing this quantum applied machine learning. I would say quantum machine learning for speech as application or language as application, no matter how we call it. So we should have to refine our problem, right? As the beginner of this slide is like, what kind of problem you want to do? You want to do the hybrid machine learning or just to see some preliminary result for speech and language processing, or you want to do something capacity based issue to dealing with this key problem in the theoretical computer science issues like the traveling salesman problem. So right now the things quantum machine or quantum computing can really have this advantage is not here. It's like here is those problem quantum computing can only deal with. And here is the classic algorithm can only deal with. But what potentially we can do is something here. So how to refine the problem can be really tricky. For example, this thing is called a bounded probabilistic polynomial problem. So if you look at his paper, he have a lot of discussion on that. But if you properly refine the problem, like the kernel problem, which we can borrow from this quantum kernel mapping and then use classic prediction to resolve our problem, we can actually to have result like this, right? So for the best classic algorithm, gather performance like from point A to point 6, but with the projected quantum kernel, you can borrow this theoretical hypothesis from here to have a good result and a much stable performance. So for the result, you can also see this Google AI block. And for the slide, I think I put the slide in the chat. And finally, I would say there's still some open problem. Like the new RIPS last year, people consider, because the kernel learning, we don't have the nonlinear activation like the neural network, right? So people are still considering some feature encoding before the variational measurement. So they can go beyond this kernel learning and to have this high dimension modeling with this feature encoding. So this is a paper from Leiden University. Another thing is like Jun's work. I think he connect this theoretical analysis as the first time to use tensor trained neural network to add this linearity and then to analysis how what the loss component can affect this kind of tensor to the quantum circuit based training as a regression problem. All right, so that's the conclusion. So for both collection algorithm data are very selective during this near-term quantum area. I would not say quantum is everything, But if we carefully select the problem we want to work on, they can be really impact. Like 10 years ago, you work on DNN. And when the large pre-trained model, for example, GPT-3 are available, combine VQC with hybrid model with classic, with combining VQC-based hybrid model with this classic pre-training is an open problem, and LLC they'll become even more important. And on speech and language classification, VQC learning right now is showing some preliminary advantage on the sample capacity. For example, you have least trainable rosy gate and the representation learning just slightly on the design you select. But I would say if we really want to have a groundbreaking like news for a speech community combine quantum machine learning, how to select a problem you can publish to Nature or Science is important. For example, if you have infinity decoding, can we use these things? And right now I think this problem is quite open. And I would thank all my collaborator and doing on this related work. And actually, this work is not in my thesis, and I just support these things as a programmer at the beginning, and gradually learn by working on these things, making my hand dirty. And I want to thank Junqi to leading me on this a lot of theoretical work. Professor Qinghui Li, at his age of 70 and still hardworking with us, like learning this quantum machine learning. I know, like in the first ICAS paper we published together, we exchanged email like 70 times when we were trying to revise this term. And Dr. Ping Chen from IBM Research to providing some computational instance. And Dr. Samuel Chen to initiate and let me know the content. Dr. Xie from Foxconn Quantum, Professor Marco, and my mentor in Google, Bolli, and Yu Cao from Academic Synca. All right, so hope you're enjoying this talk, and I also have some GitHub resource for you. For example, the QCN for speech, and the following work from Ping An company. They have a work in the IJC, and this year they have a low qubit quantum speech application tool, and Jun's work on the tensor train network at variational quantum circuit, and the tutorial from Pennyline, which is a hot AI company for quantum machine learning. They provide a PyTorch-based solution, and the TensorFlow Quantum, you can find a lot of tutorial here. And here's a reference and more reference. And yeah, hope you enjoyed this talk, and I'm happy for any questions. Any questions?
Hello.
Yeah,
hello, Huck. Thank you for an excellent tutorial. I have a question about the application of quantum kernel machine on speech classification task, on low resource speech classification task. And do you have any insight why quantum kernel machine achieve better performance? Is it just simply because it has less tunable parameter? Because if this is the case, you can always give your deep neural network less parameter. So I want to know, are there any insight why quantum kernel machine can achieve better performance on low resource cases? Thank you.
Yeah, it's a really good question. I think in this disentangle measurement, in this distant measurement progress with kernel, so they actually use a relabeling progress on the in the quantum space. For example, they are relabel this speech data with some quantum label, some quantum labels. So these quantum labels help this kernel to separate this data in the high dimension space. I think this is one reason. Another reason is if we really look at kernel-based matrix learning, there's a paper in SLT, I think last year, 2 years ago, they actually used kernel matrix learning outperform DNN-based solution. So I would say kernel matrix learning is already a good candidate model or a good candidate solution for separate this low resource speech comment. And then our idea is like, can we benefit on this kernel to make this kernel much advanced? Yeah.
Okay, so I want to add something new. Maybe it's from my research work found that if we use quantum kernel learning, it has a better representation power than the raw feature. So this means that you can use much less model numbers. With a small set of deep learning model or with other models to train to get a well-trained model. So maybe I think it's the representation capability for quantum kernel learning. Just Hong Yi said, maybe because of more larger representation power, you can use much less model parameters to get as a well-trained model.
Yeah, thank you very much for provide this idea. So which paper are you referred to? You say quantum kernel model have better representation power. May I ask which paper are you referred to?
Maybe it's send you an email to show. Maybe it's Caroline, I forgot it.
Okay.
Okay, I'll send you email to show this representation power.
Okay.
Both frequency model and quantum kernel model, that has a quantum advantage about their feature representation capability. So if we use other communication, do some classical communication task, maybe it can significantly reduce the model size.
Thank you very much.
Thank you.
Yeah, it's a really good question. For
the feature. Okay, the feature becomes more discriminative in the heritable space.
Yeah, and for the matrix learning for keyword spotting, I put that paper there. I think in this paper they suggest an idea for the matrix learning, like the non-parameter tree, like training for keyword spotting. Yeah.
Thank you.
Any other questions?
Yeah, actually, really kind of freshman in this area, quantum machine learning. So may I ask a few stupid questions.
Welcome.
The
Yeah.
kernel. Thanks. So kernel learning, where the quantum mechanics or quantum mechanics enters into the learning process is the kernel, right? When you represent the kernel, you use the quantum state. That is, you basically insert that into the kernel, the kernel trick. Is that right?
Exactly.
That's
Yeah.
Okay. All right. Cool. So, and then is there a okay? You also mentioned the transformer, particularly the swing transformer. Do you use the some properties of quantum mechanics to compute the transformer, or you're making a specific form of transformer?
I think it's a good question. Maybe I just talk too much. Sorry, talk too fast, like during that part. So if we look at this paper, so which is the image patch is the wave, phase aware vision MLP. So in their work, they just modify this MLP. I'm not sure. Are you familiar with the MLP architecture? Multi-layer perception.
Yeah, somewhat.
Right.
Yeah, I'm kind of familiar with the transformer, the classical version of transformer.
Right. So the main idea is you can see the orange orange block here. So they are associated with the token mixing progress. So this token mixing progress will associate with the PATM progress. They call these things phase aware token mixing. So here they associate this quantum computing progress. For example, they are mapping this input with some empty phase, and they will do this mixing from the real and imaginary. And I think from their architecture, all right, so
the quantum mechanics enters into the transformer through like the KVQ, the computation of KVQ. Is that the part?
Right.
And
So here they are all token about KVQ, right? So you can think of this KVQ are all going through with this token mixing progress from this input. So in the VIT, you put this input as a token, but before you fit into your MLP, you actually can get another features like from this mixing progress.
Right. Actually, because you basically replace the inner product, classical inner product, with the quantum mechanical inner product, right? Is that the idea?
No, exactly. So here is the original patches you're feeding to your like your transformer, like the MLP here, right? So if you ignore this progress, you just directly feed your token here. But here is just like
Right.
do down token mixing, and after the mixing, you give this new token to your transformer. Yeah.
Okay, so the quantum mechanical computation is performed before it enters into the classical transformer. Is that
Exactly.
right? Okay, I see. Okay, what about the during the computation of the transformer, because it is in a product, right? I mean, can you replace it with the quantum mechanical computation, because that isn't also in a product, right? Would that do anything?
It's a good question. I think this paper like mentioned how to do these things called a quantum attention. So from this this paper, there's following work called the quantum attention to reduce the sample capacity, but due to the time constraint, I didn't cover here. Yeah, there's another way to introduce this quantum inspired computation for transformer based algorithm. Here I select this paper. It's
cool.
like it's one of the SOTA result on the ImageNet. Yeah, classification. Yeah, it's the
Cool,
I think it's
cool.
the SOTA result for 2 or 3 months. Yeah.
Cool. That's great. Yeah. Thanks so much. I have another question. So adding the nonlinearity. Yeah, I was actually wondering about that. I suppose let's say the classical neural net, you have this ReLU function, right?
Exactly.
So in the quantum mechanical version of the neural net, how do you produce the ReLU or something similar, the nonlinear function?
It's a really good question. So I know if a lot of people they heard the quantum circuit today, we still don't know how this get computed before you write the code by yourself. But the real idea is that you have a tensor product which is do the rotation in the tensor space. So if you do the quantum circuit training, the nonlinearity they don't have this kind of nonlinearity. They just suppose you do the tensor like a projection in a high dimension space, you can mapping back to the right direction. So that's why they're adding some nonlinearity by the feature encoding or some different way like the TTN. But right now they don't have the ReLU if you directly do the like quantum circuit based end-to-end quantum circuit based training. But if you add this quantum circuit training with some DNN algorithm, you have your ReLU as the activation. So in the hybrid model, you have this nonlinearity. But for the pure model, you yet have that. So that's why they need the feature encoding in before you fit into the like the tensor rotation network. Yeah.
I see. So the full quantum, you're saying, okay, just want to summarize what you were saying. The full quantum version does not have the kind of intrinsic nonlinear function. Is that right? Is that what you're saying?
Exactly.
Just want to make sure.
Exactly.
Okay. Yeah, that's what I figure, because all the quantum mechanical operators are linear.
Yes. And from the physics community, they will consider quantum circuit just a special form of tensor network. So that will make this easy, this understanding much easier. Yeah. Right.
So you have to inject the nonlinearity from outside, right? Extrinsically. Is that right. Correct?
Yeah.
Okay. Got it. And then you have a hybrid. If you have a hybrid version, then you just use the classical ReLU function, and then inject the linear function before and after that, right? Yeah, that's correct. Got it. But the linear function is in the high dimension space, so it's not, the understanding is not precisely to the classic linear modeling. Yeah. Okay, and then you mentioned the rotation. So the rotation, can you repeat that? Where do you insert the rotation into the, which part you insert the rotation into it?
Yeah, it's a good question. So for example, you have a input like this, you can have a ball like this, right? Right, so
Yeah, I know the block sphere.
yeah. So you have
so
you
then
have this,
okay.
right. So you have this like the trainable angle by the circuit, right? So for example, if you look at right, okay. Let me find the random quantum circuit. Okay. Yeah, if you look at one quantum circuit like this, these things are like those things are some rotation here. So
Yeah,
if you,
so the Pauli matrices, right?
right. So there's some Pauli matrix here. Then if you're just trying to, for example, you want to design a new resonate for a quantum rotation gate, the zoom to design is how you connect this rotation gate. So in this paper, actually, I think the main idea from empirical perspective is they find out you can simplify this computation by have the wiring like this. So by have a wiring like this, for example, you connect this gate two by two like this, you can have a universal approximation as a dense layer. So that's why this paper got a lot of attention. Yeah.
I see. That's interesting. Okay, cool.
Yeah, so let's say like you can have your own connection from here to in the input or to use different kind of quantum gate you are coming from, if you're coming from the physics community.
Yeah. Physicist. So okay, cool. Yeah, I think anything. Oh, okay. So just last question. Anything that the does the quantum mechanics offer any better optimization tools than the classical version? Let's say the stochastic gradient descent and everything else, all the other methods. Does when you incorporate the quantum mechanics into this the whole structure, does it give you more kind of optimization tools? Maybe it's the variational quantum circuit.
Yeah, so I would say like both classic and quantum circuit, they still use HGD for training. So if that's the like computation tool you mentioned, the HGD is the same, but the way they use HGD is different. For the classic machine, they do the backpropagation. For the quantum circuit, they do things called gradient shifting training. So if you directly Google the gradient shifting training, there's one kind of black box algorithm to train this black box model. For example, if I have a black box, I don't know where I should go this gradient descent. The idea then you can add a little bit perturbation from your starting point and calculate the difference from this perturbation in your original plan to have a direction for the gradient descent. But these things is not computational economic. So that's why for training a quantum algorithm, they usually take much more time. But the gradient is the same. You still do the gradient, you still do the HGD, but you just didn't do the backpropagation. Yeah. Does that answer your question?
See. Yeah. What's the name of it? The gradient shifting or gradient? What? What's the word?
I think
gradient shifting.
Yeah, I think if you look at this paper, I think it's from physical review. Yeah, you will find out how they actually train this model. I'll put it in the chat. Yeah.
It's very similar to the finite difference. It means that is
Yeah,
out input, negative input, as we see the difference will be divided by the distance.
Exactly. I put it here in the chat. It's a question.
Cool. Yeah, that's great. Yeah. Wow. Thank you very much.
Yeah, hope this tutorial will be clear. Yeah.
Yeah. Actually, are you gonna give the slides? Both of you leave the slides somewhere or something.
In the chat. I can share it here again. Yeah. And I have all the image reference. If the image is without source is drawn by myself, yeah.
Okay, great, thank you. And then these references are all in the slides, right?
Exactly. All right, so I will be in Singapore, so feel free to contact me and Professor Lee. I know Professor Lee himself is still interested on the quantum machine learning. Yeah.
Great, thank you very much, Huck,
Yeah.
and also Jun.
Yeah, thank you for your time.
You're welcome.
Yeah, take care.
Okay, that's good. We'll see you. We'll see. And that was this tutorial.